All right, a quick look at some of the properties that bear out from intermolecular forces, and did a little activity in class today to exhibit these different properties, and now we're going to try to get some of those observations down into our notes for future reference. So let's just take a look at the first one. This whole concept of like dissolves like. We really looked at this when we did the chocolate lab, and we saw that sugar dissolves in water, and then we saw that the sugar did not dissolve in the oil. But on the other hand, the cocoa butter did dissolve a little bit in the oil. So we want to figure out why that happens. Well, it's simply because substances that have similar polarities will dissolve in each other. If you look at the picture on the right, you see a very common occurrence, trying to put oil in water. If you've ever looked at some Italian salad dressing, you'll notice that it separates out. And the oil layer is going to go to the top, whereas the water layer is going to go down towards the bottom. Or the vinegar layer will be on the bottom. These two things do not mix because oil itself is nonpolar. It has really long chains of carbon hydrogens, so methyl groups, and we can see that by just carbons kind of attaching to one another over and over and over again. Hydrogens coming off of them. So there's all of these nonpolar bonds. This is a very symmetrical molecule. It's kind of what the oil looks like. The oil will look kind of like these molecules. And so that molecule is very, very nonpolar. On the other hand, the water molecule, the stuff on the bottom, is very, very polar. It's one of the most polar molecules that we talk about. And so there's a partial negative side. There's a partial positive side. And if the water and the oil get together, well, there's no partial positive or partial negative on the oil, so there's no reason for there to be an attraction between these two molecules. And hence what happens is the more dense substance, which in the case of these two things, the water, will actually drift towards the bottom. So the water's more dense, and so it'll drift towards the bottom, and the oil will rise towards the top. Now, it doesn't have to be just polar and nonpolar substances that exhibit this. Try to go to the next slide here. There you go. Polar substance will actually dissolve other polar substances, but will also see polar substances dissolving things that aren't polar at all, but are more commonly called ionic. And this is called the ion dipole attraction. So again, if you've got a water molecule, and you've got a whole bunch of them, right? With a negative charge on the oxygen, positive charge on the hydrogen. And then over here, you've got sodium chloride. So here's my Na, and here's my big chloride ion. Right? The sodium's positive. We will get an intermolecular attraction between these two. And that's an ion dipole attraction. So we say like dissolves like, and we mean that. We mean that if the substance has a positive and negative charge, there's a good chance that it's going to dissolve another substance that also has a positive and negative charge. Oil doesn't, so it's not going to work in the case of oil. Nonpolar substances do, however, dissolve other nonpolar substances. And again in class we saw that with the addition of the ethyl ether and the iodine molecules and saw how those dissolved in each other. All right, so other than like dissolves like, one of the other properties is called viscosity, probably a term that you've heard before. And if you look at the diagram in the lower right-hand corner, you'll notice that you've got two test tubes and they're being dumped out. The one on the left is a substance with very high viscosity, and the one on the right is a substance with low viscosity. And you can see the low viscosity test tube is almost empty. It's almost dumped out all of its stuff. You see the little watch is taking time, so these things were dumped out at the same time. The high viscosity, the stuff on the left, it's taking a while for that to pour out. So if you want to think about common materials, you can think about the high viscosity stuff being honey, and the low viscosity stuff just being water. Honey would take longer to dump out than the water would, just because of the intermolecular attractions that occur inside of the honey itself. So to define viscosity, we just can simply call it that it's a fluid's resistance to flow. If something resists flowing, it has a high viscosity. Vice versa, it's got a low viscosity if it flows really well. Now, this is usually directly related to molecular size. So if you've got a molecule that's tremendously huge, it usually has a higher viscosity. So melted plastic, for instance, has a high viscosity. Oils typically have a little higher viscosity. They're a little bit more viscous. Smaller molecule things like rubbing alcohol or water, they typically have a lower viscosity. And the simple reason for this is that things with a large molecular size have more surface area, so there are more chances for intermolecular forces to bind adjacent molecules together. This is also, the viscosity itself is indirectly related to temperature. So what that means is that as the temperature increases, viscosity of a substance goes down. So if you've got some honey in a cup or a jar, and you want to get that honey out of that jar, and it's maybe cooler, and it's really hard to scrape out, you just got to heat it up a little bit, right? And heating that up, in a sense, what that does is that makes the molecules move fast when they're hot. And thus what that does is that breaks apart the intermolecular forces. And that allows that substance to flow a little bit easier. A third property we'll take a look at is surface tension, which is just a really cool property. And there's a lot of neat demonstrations that you can do with surface tension. Just basically defined as the cohesive forces between liquid molecules. So if you think about a liquid molecule, and I've got a sample here in the left hand with the picture here, we're going to think about all these little spheres being water. And when water is surrounded by a whole bunch of other water molecules, like you see in the lower right-hand corner of this picture, each one of those water molecules kind of attracts to one another. So the center one is attracting to all of the ones around it. Okay, all the ones around it. But that happens at the surface too. But now the issue at the surface is there are no molecules up top. Okay, it's kind of like the voided area up there. So the attractions that occur between the molecules at the surface, called these cohesive attractions, are very strong. Okay, and what that allows for is you've got an object like a water strider, which is the bug over here, who has feet that have a large surface area. If you could zoom into his feet down there, so I don't know if it's a male or a female. I don't know my water strider sexing abilities too much. I don't know how to tell which one is which. But they have a large surface area in their feet. And so what they can do is they can take advantage of water's ability to have these strong cohesive forces at the surface, and they can actually walk right on the water. It's kind of a nifty little trick that they have. And so again, we could say that this is indirectly related to temperature, right? If we heat up the water, what's going to happen is these cohesive attractions between the molecules will start to break, they'll start to fracture, and then our poor little water strider is going to like fall into the water, and he'll get eaten by a giant fish that will come up and consume him, and that'll be terrible. Okay, so we want to make sure that the water stays cool enough for that poor little water strider. All right, the last property to take a look at then is phase changes. And we're actually going to have an entire lab on phase changes and how intermolecular forces affect how phases can change between substances. If a group of molecules has strong intermolecular forces, in order to break those molecules apart, we're going to have to actually put in a lot of energy. So a group with really strong intermolecular forces, like a whole bunch of water molecules, we're going to have to put in a ton of energy in order to break those bad boys apart. And so if you look at that, look at the boiling point of water, it's 100 degrees Celsius. That's really, really high. On the flip side of that, dihydrogen sulfide, which is way down here, the hydrogen sulfide bond is not nearly as polar as the oxygen-hydrogen bond. And so we don't have to put nearly as much energy into breaking that bond. And so we can make that stuff, a gas, a heck of a lot easier. In fact, about negative 50 degrees Celsius, and we can turn that stuff right into a gas. So that's pretty cool, right? So the strength of the intermolecular force is really the do-all, end-all in telling us what temperature that particular substance is going to boil at. And you can kind of follow this graph and see how those relationships work throughout. All right, those are properties that stem from intermolecular forces.